The last video was an example of using buoyancy in problems where something sinks or where something floats. And I want to look at this again, but with a slightly different situation. So I want to look at buoyancy in terms of lift. Let's do a problem with a hot air balloon. So this is a buoyancy example. So a hot air balloon. So maybe we've got a hot air balloon. A hot air balloon works a certain way. First, we need a size. For a hot air balloon with an 8-meter radius, which is actually a pretty reasonable sized hot air balloon. So let's say 8.3 meters. Is a good average size. This gives a volume of the hot air balloon. It is approximately spherical, 4/3 pi r cubed. It's going to give us 2,400 cubic meters. This is about the size that you would expect for a hot air balloon for 3 or 4 people. So a hot air balloon works like this. We have fire right here. And that's going to heat up the air inside the balloon. Because the air inside the balloon is heated, that means that the air inside the balloon, the particles of air want to move faster. There's a vent at the top, so those particles kind of bounce out. So what we end up with is an inner density that's going to be lower than the density of the air outside. So the density of the air inside a hot air balloon at about 100 degrees Celsius works out to be about 0.9 kilograms per cubic meter. The density of the air out here is about 1.2 kilograms per cubic meter. So we have a lighter density, smaller density inside the hot air balloon than outside the hot air balloon. This means we are going to have some amount of lift. Now the hot air balloon itself does have mass, so we'll have to take that into account. But let's grab some of those values. Okay, I found these values pretty quickly. The envelope, that is the part of the balloon that's what the balloon itself is made of. So it's like if it were empty, that's what the balloon fabric part would be. The basket, that's straightforward. The burner is the part that's burning fuel. The pilot and the passenger is saying together maybe 150 kilograms. Let's go with this. So we get a total mass of 315 kilograms. Now we need to lift this thing. I have a free body diagram, the start of one. Going downward, I have an mg, and I'm going to call this my 315 kilograms. I also have an m of the air inside the balloon times g, and then I have a buoyant force upward. I'm going to call upward my positive direction. And here we go. My sum of forces. I've got this buoyant force up minus mg down minus m air g down equals m plus m air times acceleration. I would like this thing to not quite go, and I want to solve and see how much extra mass maybe I can get, or let's just find, you know what, let's solve for the sum of forces and see if we can get some lift out of the deal. The buoyant force, F buoyant, is equal to the density of the fluid that we're in times the volume of fluid displaced times gravity. So we're going to need a couple more items. We've got the volume of the hot air balloon itself. We're going to need the volume of the basket too. That volume is small. It turns out this is about 1 cubic meter, a little bit more. We've got the person, we've got the burner. Overall, this whole total volume here is something like 2 cubic meters. And it's rounding up a bit, but that's my displaced volume. I'm going to go that for my buoyant force. My mg, I've got that. My mass air inside the balloon is going to be the density of the air in the balloon times the volume of the balloon. That works out to be, I've got my 0.9 kilograms per cubic meter times 2400 cubic meters, and that's 2160 kilograms. It's a lot of air. Now I need to start putting pieces together. My buoyant force, my density of my fluid, is the fluid around it, that's the air, 1.2 kilograms per cubic meter, times the total volume displaced. The total volume displaced, I've got my 2400 cubic meters plus 2 more. So let's do that, 2402 cubic meters, and then times gravity, so times 10 meters per second squared, and that gets me to a value of 28,800 newtons. It's a lot of lift. Let's see what we are working against. We have 28,800 newtons minus 315 kilograms times 10 meters per second squared minus 2160 kilograms times 10 meters per second squared, and we end up with a net force, so this is my net force, of 4,050 newtons. If I convert that to a mass, that means I can still lift another 405 kilograms. At this volume, at that density, I get a net upward lift